Okay, so let's talk about how to interpret the data. Okay, so going back to this figure that's in your book, what this is a slice of the solenoid. So a vertical slice like this. So if you would imagine, this guy's a solenoid, right? So it's like this. If we take a vertical slice like so, cut this guy in half, then if you're looking into this back face, you'd see, this edge here. And what this is the arrow convention. So this means, remember, we have current running through this guy in either clockwise or counterclockwise. But this guy, arrow convention, what this means is that when I look on this side, I see this is the arrowhead. So this is, if someone is trying to shoot me with an arrow, I'd see the arrowhead coming to me. And then if I was trying to shoot someone with an arrow, then I'd see the tail of the arrow. So arrow coming this way, arrow going this way, which means that the current, in this case, is coming like this and wrapping around like so. So this would correspond to current going in this direction, right? So this is counterclockwise, right? And so to verify that, you see that if it was going counterclockwise, it would be in this direction. So if I wrap my fingers in the direction of the current, then I have the field in the middle pointing up, which is what we have here, right? So we have that, and then in the solenoid, what you have is the field in the middle. Is more or less straight up and down, but as you go off the middle, you start to have this fringing effect when you get to the edges of the solenoid, right? And so, if we're to take, because the field is a vector, and it can be broken down into its constituent components. Here we have figures in 2D, so we're going to have two components. So here we have an axial component and a radial component. And the magnitude of each component depends on the location at which you are on the solenoid. So for instance, you can see if we're focused at this point here, you'd see that the total field is just radial, right? Because it's, there's no axial component here. And then by the same token, if we come here in the middle, we'll see that the total field is axial and there's no radial, right? But these are components, they depend on where you're on, the location that you're on in the solenoid. But, so let's talk about the first one, the center one we did. So what we did is that we have this sensor, again, and what we have here is, in essence what we're doing is we have the sensor somewhere down here, and then we pull it up all the way, and then along the way it keeps track of the field. It keeps track of the axial field, and it keeps track of the radial field, right? Now when we do the center run, when I did the data that I did, and it wasn't great, but what you saw for the axial field is we had just a single hump. So it had something like so, right? Symmetrical, they're not supposed to be symmetrical, not zero. But what's important is just that you have a single hump. Now why is that? So if you look at, let's take this field line vector over here. So if you look at the field line down here, right? If we just focus on this portion, we can see this guy has its constituent components are a radial field pointing to my left, and then an axial field pointing up. All right, and then now if we follow the same field line and look at it up here, you'll notice that the axial field points up still, but now the radial field points to my right. And so you see that there's an inflection point in the middle where the radial field switches directions. All right, so down here it's pointing to the left, up here it's pointing to the right, but the axial field is always pointing in the same direction. So it's up here and it's up here as well. All right, so what does that mean? That means the axial field never changes directions. All right, but it grows in amplitude. Why? Because, like we said, down here, if you look at this portion, we have nothing but radial field right at this point. All the fields just this way. In the middle, we have nothing but axial field, right? But the total field is a combo of radial and axial. And so we have maximum axial field when there's no radial field. Where is there no radial field? Right here in the middle, somewhere here in the middle. So when you're in the middle, you have the total field will just be axial, more or less, right? And so now if you look at the center run, so what we did with the center run is we had a sensor like so, hold it up like this to the middle, and you'll see that in the middle, the field line is only axial, right? You see that there's no fringing, there's no bending of the field in the middle. So it's more or less straight up and down. And so in the middle, the field is only axial, right? And then the component grows from nothing down here. So all the way down here we have nothing. And then it's going to grow, it's going to hit a max right at the middle, somewhere over here. We're going to hit max value of axial field. And then it's going to decay and then hit zero again all the way up. So, which is why we have this graph over here. So the starting position is somewhere over here, way below solenoid. We have no axial field. And then as we pull the thing through the solenoid, the axial field magnitude is going to grow to some max value. This max value here corresponds to, this one right in the middle. Right? And then as we go past the middle and go all the way up the solenoid, this thing again goes to zero. And so we have just one, we have just a single hump, right? So, and this hump is either positive or negative depending on the direction the current is going. So you can imagine if the current was reversed so that the current was going clockwise, then this guy would have a single hump still, but it would be reflected across this axis over here. Right? And then now what's going on with the radial field? Now we've said that in the middle, the total field is in essence just axial field, which means the radial field is more or less negligible, which is why, if you recall, when we looked at the tabs on the computer, this, I forget what the amplitude here was, it was maybe about 20, I think it was about 20 millitesla, right, for the axial field. And then when we looked at the radial field, it looked something like, something like this. It's basically noise, but the amplitude was, something like 0.00, something like this. So it's super tiny. It's, in essence, should be zero. If we had it perfectly, because we're doing this thing, manually by hand, there's bound to be some experimental error. But if we had it perfectly aligned in the middle, this thing should give you basically zero, because there's no axial, there's no axial field. Yes, there's no axial field when there's no radial field, I'm sorry. There's no radial field as you pull the sensor up from the middle, because everything is just axial to the middle, right? And so this is what the center looks like. You have a single hump for the axial field, hits max amplitude, depending on the direction of the current, or and so the direction of the field, and then the axial field should be more or less non-existent. Okay. Now, so what happens when we look at the east side of the wall? If I could get rid of this for a second. Let's draw this real quick. This thing here is B, and this thing where it's X. All right. So when we look at the east side of the wall, again, we're not going to flip the orientation of this guy, so we're going to keep it, for our runs, we did it with the angle facing south. So this is north is straight ahead, which means west to this side, east to this side. And so the east side of the solenoid would correspond to this side of the wall. So what I'll do, the procedure is same thing, but now instead of pulling it through the middle, we'll have it down here somewhere and then pull it up. And then all the while you'll raise the east side of the wall as you pulling the thing all the way out. Right? And now what's going to happen this time, you'll notice that when we're out here, right, we said that the radial field is a maximum at this point here, it's a minimum here, and vice versa for the axial field, right? And so what we'll see happen is the axial field will look more or less the same. So it'll grow from zero, right? So we had a zero way down here. We hit a max from here, somewhere here in the middle, and then a min again when we're all the way out. And so the axial field is going to look more or less the same. I should actually kept what I had before, but just a single hump, right? But now what's happening? If we look at the radial field now, though, right? So the radial field, you'll notice that down here, so it'll grow from zero, but the radial field hits a maximum somewhere over here, right? So somewhere in the middle, between here and here, we have a maximum radial field. And then it goes to zero at the middle. So at the middle, the field is totally axial, so there's no radial field here. So we have a zero here, a zero here, and a maximum somewhere in between these two guys, right? And now what's going to happen is we have an inflection point in the middle, and then the axial field, radial field, amplitude is going to grow again, and then we'll hit a max somewhere over here, and then a zero when we're all the way out. So what will end up happening is we'll have two peaks with the radio field. And the direction and the polarity of the peaks depends on which side of the wall you're looking at. So in this case, if we're looking at the east side of the wall using this convention in this picture, so again, this guy, let's talk about this again. So this guy says positive axial is this way, positive radial is this way. And so if I have my handle like this, it means when I'm down here, as I pull this guy up, you can see that the radial field is pointing to my left, which corresponds to this guy's positive axis, right? So the radial field is going to go from 0 down here, grow to some max value, max positive value, because it's pointing to my left when we're down here. Go back down to 0 here in the middle, because we have no radial field in the middle. And then grow again, but now at this point, you'll notice that the radial field is pointing to my right? So it was pointing to my left down here, it's pointing to my right down here, which means down here, the radial field is going to be read as positive, using my convention over here. And then when we're up here, it's going to be read as negative, right? And so that's why we have two pulses for the, or 2 peaks for the axial, for the radio portion. And so when you look at the graph, we have two humps, positive hump to begin with, and a negative hump at the end. And so the graph here is going to look something like this. It's going to go back to 0 in the middle, and then negative hump, and then it's going to go back to 0. All right, and so we'll have these 2 humps. So this would be the east, right down here, east radio field. So yes, east radio field. So east axial will be similar to the center run for the radio field. Now you'll notice that, first of all, we have 2 humps, and then the peaks here would be significant. So in the previous run, we did the center run, the peaks were, point, 0.02 something, so it's something negligible. Here, these are going to have some, significant amplitude, and you should have these values in your data file, right? So this is what the east field looks like. The west side of the field, or the west side of the solenoid, do the exact same thing. And so now if you follow the same analysis, we're going to bring this sensor down here, pull it up to the west side. Using the same analysis, you'll notice here that the radio field at the bottom is pointing to the right, which is opposite the east side. And then at the top, it's pointing to the left. And so if you look at the west run, so now for the west run, or no, let me keep this here, east, and then I'll do another graph here. And you want for west radio, right? And so, whereas we had a positive peak first for the east side of the solenoid, we're still going to have two peaks, except now this thing is going to start at negative, hit 0 at the middle, and then finish as positive. So this is like a mirror image of this guy reflected across the now this axis over here, right? So we have this thing, and again the amplitudes here are significant. You should get that from your data file, right? So we can see that the east radio field is a mirror image, or it's a mirror image reflected across this axis of the west, right? So this is what the east looks like. This is what the west, this is the radial stuff, west looks like. And then you can imagine, now for the east reversed, what we said is we'll do east again, except before we do that, we'll reverse the direction of the current. So I'll let you guys, do a drawing where now instead of the current going, counterclockwise, it's going clockwise, which means that all these arrows, now they're pointing the other way, so you'd have to flip. Instead of this guy pointing this way, pointing down, and all these guys pointing down. And then you'll do the analysis for the radio field here, and then you'll get some data for the axial field and radio field. And then you have to make some comments about what you see as far as the radio field goes between the west and the east reversed. Yeah. And so that's the analysis of the graphs, right? And now the last thing we'll do is we have our current value that we got from the computer. So we have we have I, we have R, it's in the table, we have N, and we have a field strength reading from the solenoid, from the sensor, for the center one. We're going to use the center one. So the center one gives you specific reading. It's going to tell you what the field strength was here in the middle, right? So we have this reading here. And so now for the last thing, we need to get these two values. So the single coil approximation and the long solenoid approximation of it. So what we'll do is we'll plug in U naught. We'll plug in N, which all these things we know. We'll plug in I that we get from the computer, R, calculate this guy. We'll get a bound value for a single coil, right? And then we'll come over here and plug in the same things for this equation. U naught here, N, tiny n, which is coil and density. Remember, so this is N over L, which is over here. So N is 600, L is 2.5 centimeters. I'll say that the meters. You get this number over here, plug that into here. Use the same I value from before, and this will give you some number. So we'll have two values. One that's a long solenoid approximation, one that's a single coil approximation. And then we have a reading from the actual sensor, right? And then we do a comparison. And then we want to say, is our solenoid, is it closer to being a single coil, or is it closer to being a long solenoid based on the values that we have? That just depends on the difference between the values. All right. And I think that's more or less it. If you guys have any questions, we will still be here. So if you log into Zoom during just regular class hours, we'll be here and we can do some more demonstrations if you like for the software, for instance, or the hardware, and you know how things work. For instance, I'll talk about any of the things that are not clear. And yes, and I hope you guys stay safe and take care of yourself.